So I've more or less got the basic notions of algebraic groups in place. I'm going to do one more basic topic today, and then I'll be all set with the language that I want to try and pass from algebraic groups to Lie algebras starting next time. But let me see, what have we got so far? I've given you some first examples of algebraic groups. The most important ones for us are the general linear group, special linear group, that's determinant 1, the special orthogonal group, and the symplectic group. And then I've proved one decent theorem so far, which is this analogue of Cayley's theorem for algebraic groups. So I proved this thing last time, that every algebraic group is linear. And the proof was a little bit long, but the basic idea is simple enough. You find a finite dimensional vector space that the group acts on by looking inside the regular representation. That's this action on its coordinate algebra. Okay, so today I've got to just cover just a couple more kind of basic topics. So one thing I didn't say yet from affine algebraic geometry, I didn't talk about irreducible components. So if you have an affine variety, it decomposes uniquely as a finite union of what are called irreducible components. So I have talked about what it means for an affine variety to be irreducible. That's a purely point set topology notion. But in the case of an affine variety, there's also an algebraic characterization of being irreducible. It's if and only if the coordinate algebra is an integral domain. But the notion irreducible, it's just a purely topological notion. So in fact, you can define an irreducible component of any topological space. It's simply a maximal irreducible subset, where I mean irreducible for the subspace topology. So because if you have an irreducible subset, a subset's irreducible if and only if its closure is irreducible. Those irreducible components are automatically closed subsets. And so this decomposition, in fact, this makes sense in any topological space, but you need some finiteness. What you need is that the topological space is Noetherian. So a topological space is Noetherian if it has the descending chain condition on closed subsets. So there's kind of a simple proof of this decomposition into irreducible components. It's just a point set topology style proof. And any Noetherian topological space decomposes uniquely as a finite union of its irreducible components. For an affine variety, the Zariski topology on the set X is a Noetherian topology. That just follows from the Null-Schlellensatz, because the closed sets correspond to radical ideals, and the coordinate algebra is Noetherian. That means it has the ascending chain condition on ideals. So I'm not going to prove those things, but we're kind of in business here. Maybe it's worth just kind of muttering that although this is a result that I prefer to just prove using point set topology style arguments, you can also think how to say this in terms of the coordinate algebra. And so if you translate that, you end up getting the notion of the primary decomposition of a commutative ring, which can be generalized vastly to Noetherian rings. But we only need this special case for the sort of coordinate algebras that come from affine varieties, these reduced, finitely generated commutative algebras that we've got. Okay, so that's what's going on. So now I want to think about what does irreducible component look like for an algebraic group G? So that's the first lemma today. It kind of answers this question. So now G is an algebraic group. And in fact, the identity element belongs to a unique irreducible component of G, and I'm going to denote that by G0. This G0 is actually a closed normal subgroup the irreducible components of G are exactly the cosets of G0 in G. In particular, because Noetherian topological space has finitely many irreducible components, this means that the index of that normal subgroup G0 in G is finite, and in fact G0 is also the connected component of G containing E. So let's see, there's a few things just to say about there. Why is this a consequence? It's immediate that if you're irreducible, you're connected. So the G0, the way we've just defined it, it's irreducible, so it's definitely connected. But you see, G0 is closed in G, and because its index is finite, the complement of G0 in G, that's a finite union of other cosets, which are other irreducible components. That finite union is closed as well. So that means that actually G0 is both open and closed in G, and it's connected. So actually it's the connected component of G containing E. So I guess because of this, you usually call G0 the identity component of G, and we're often going to talk about connected algebraic groups. So we're going to say that G is connected, a connected algebraic group. Well, of course, because G0 is this connected component, that's just saying that G equals its identity component. And just for good measure, the final part of the lemma is also easy. Any closed subgroup H of G of finite index contains the identity component of G. So we're going to prove this. There's a bunch of fairly simple arguments. It's not a bad proof at all. But I guess the kind of message of this is that if you start with a general algebraic group G, you can always pass to its identity component, which is a connected algebraic group. And parts 2 and 3 of this lemma tell you that that's a closed normal subgroup of finite index. Being normal, it means you can look at the quotient group G over G0. And this then is a finite group called the component group of G. So this lemma, it kind of gives you this sort of first reduction into thinking about the structure of a general algebraic group. You can always split that group into a connected algebraic group and a finite group. Next time when I'm starting to move towards Lie algebras, the stuff I'm going to be doing then, it really only gives you any information about this connected component. It's maybe worth just sneaking in a couple more little facts. I mean, if your group G is finite, well, then this identity component, it is just the identity element, and so it's really not interesting at all. So you see, connected finite groups, they're just the trivial group. So this is why this idea of Lie algebra only starts to emerge when you leave finite groups and go to algebraic groups of positive dimension. Things like GLN, SLN, they're obviously irreducible varieties. SLN is just a full affine space. GLN is an open subset of full affine space. So they're obviously irreducible. The coordinate algebras are integral domains. Less obvious but true, SP2N and SON are connected algebraic groups. And I give you a kind of idea of how you might prove that for the symplectic group on the homework. The proof, I know, you have to actually use some group theory about that symplectic, about the structure of the symplectic group. The orthogonal group is not connected. In fact, the connected component, the identity component of the orthogonal group is the special orthogonal group, and then the component group, that's plus or minus 1, at least if you're not in characteristic 2. So we've kind of seen this before, so that's a sort of special case of that short exact sequence. Okay, let's prove the lemma. So the first part, we've got to prove that there's a unique irreducible component containing the identity. So let's take two irreducible components of G containing E. So we can look at multiplication. So that's just the restriction of the multiplication in G. It gives us a morphism of varieties, so a continuous map, in particular, from X cross Y to G. Now, X and Y, they're both closed in G, and they're irreducible. So those guys are irreducible affine varieties. And I haven't said this before, but the product of two irreducible varieties is again irreducible. So X cross Y is irreducible. That's actually kind of a purely algebraic fact, because the definition of product is really tensor product of coordinate algebras. So this amounts to showing that if K of X and K of Y are integral domains, that tensor product is an integral domain. And I'm not going to go through the detail of the proof, but I just want to point out that the fact that the field is algebraically closed is kind of crucial here. It's quite easy to come up with examples of tensor products of integral domains over fields that are not algebraically closed, like C tensored over RC. That's actually not an integral domain. So the algebraic closedness of the field K is kind of crucial for this thing. I think you usually prove it using the Nullstellensatz, and that rests on being over an algebraically closed field in the first place. That's why algebraic closure is important in everything we're doing. Okay, so we've got this multiplication, it's continuous, so that implies that the product xy, that's the image of M, is irreducible, because continuous maps send irreducible spaces to irreducible spaces, and so actually the closure, that's a closed irreducible subset of G. And because Y contains the identity, X lies in there, and X contains the identity, so Y lies in there, and X and Y by definition are irreducible components, so they're maximal irreducible subsets. So the maximality of X and Y actually implies that they're both equal to XY bar. And so lo and behold, we've proved X equals Y. That's the uniqueness that we needed for part 1. So now we know that G0 is characterized, it's the unique irreducible component of G containing the identity. Okay, so now for 2, I want to show that G0 is a closed normal subgroup. Of course, it's closed because it's an irreducible component. So if I apply 1 with x being equal to y being equal to G0, you get right away that G0 is equal to G0, G0 bar, which shows that G0 is closed under multiplication. It contains the identity element by definition, so to show it's a subgroup, all we've got to do is show that it's closed under inverses, but the group inverse map, I, that's a homeomorphism. All we need right now is that it's continuous. So if you apply it to an irreducible component, you get an irreducible component. And of course it contains E. So actually I of G0 is G0 by part 1. So yeah, G0 is closed under inverses, and so that proves that it's a subgroup of G. I want to get that it's a normal subgroup. But if you have an element of G, then there's this conjugation map, conjugation by G. That's again a homeomorphism. So if you conjugate G0 by little g, this is again an irreducible component. And it contains E. So by part 1 again, this is exactly the unique such component, and that implies that G0 is actually normal in G. Okay, so that's everything for part 2. For 3, let's let X be any irreducible component of G and take an element. Well, so left translation, so left multiplication by X inverse. So this is the map from G to G, sending an element to just X inverse G. This is a homeomorphism. So it sends irreducible to components to irreducible components. So that translation, X inverse X, is an irreducible component of G, and now it contains E. So it must be the unique irreducible component of G containing E. So this shows that yes, X is a coset of G0. And similarly, you show that every coset of G0 is an irreducible component, being a translate of a component. This shows that the irreducible components of G are exactly the cosets of G0, and since this is a Noetherian topological space, there's just finitely many irreducible components, so this gives the finite index of that normal subgroup as well. And then, as I already explained, it follows that G0 is also the connected component of G containing the identity. So we're nearly done. Then finally I've got to take a general closed subgroup of finite index. Being a closed subgroup, H is an algebraic group in its own right, so I can apply what I just did and talk about the identity component of H. So this is finite index here and finite index here. So this has finite index. And that implies that this H0, it's closed in G, and its complement is just a union of finitely many other cosets of it. So its complement's closed. Oh, so that implies that H0 is open and closed in G, and it's connected. It's irreducible, so it's connected. And so that implies that actually H0 is a connected component. of G. Let me see, I just need a tiny bit more room. So actually, that means that H0 has to be G0, the identity component of G, and of course then, because H0 is contained in G, in H, that means that G0 is contained in H, and that finishes the proof of the lemma. Okay, so that's lemma 1. So that's passing to connected algebraic groups by taking the identity component. Lemma 2. So this is a simple but very useful little fact. So again, G is an algebraic group, and now I want U and V to be just any dense open subsets. And then the lemma says that actually then the group G is equal to the set-wise product U times V. So this is kind of cheap and easy. All we have to do is we have to take any element of G, and we've got to prove that I can write this little g as a little u times a little v, an element of u times an element of v. So let me see. What I'm going to do for this is I'm going to look at V inverse. So I've applied the inverse map, which is a homeomorphism to V. So V inverse is also dense open. And then I'm going to multiply on the right by G. So that's this translation. That's a homeomorphism as well. So this V inverse G, that's dense open, as is U. So these are both dense in G. So the intersection is not empty. So I can pick some U in U so that U also lies in V inverse G, which means what? That means that this little U is a little V inverse G, and I always get this the wrong way around. For some V in V, and I always get this the wrong way around, so let me switch U and V around. Apologize for that. So I can get some V in V, so that V is in U inverse G. So that means, what does that mean? That means that this V is a U inverse G for some U in U, and that implies that this G is UV, and okay, there we go. Okay, so other than switching U and V around, that was good. So this lemma is needed in the proof of the next one. So now let G be an algebraic group. And H be any subgroup, not necessarily closed. So H needn't be an algebraic group in its own right. Then actually the closure of H and G is also a subgroup. Moreover, if H contains a non-empty open subset of its closure, so open in the subspace topology, then H equals H bar. Okay, so let's prove that, and we're going to need that then for the theorem that's about to come. So let me first show that the closure of H is a subgroup. So take an element, little h in H, as the map sending G to HG is a homeomorphism. You deduce that HH bar is equal to HH bar. Okay, so I can pull this outside taking closure because it's a homeomorphism. But of course, HH is just big H. So this shows that if I take H bar and I multiply on the left by H, that's just H bar again. Now take an element of the closure, and let's look at the translate big H times little h. So that's in H bar by what, so by what we just showed, that's a subset of H bar. So now that means that the closure of HH is also lying in H bar because that guy's closed. But this is just H bar H because that right multiplication is a homeomorphism. So this shows that H bar is closed under multiplication. It's immediate that H bar contains the identity, and as I is a homeomorphism, I of H bar is I of H bar, and that's just H bar because H is a subgroup, so this shows that H bar is closed under inverses. And so now we've proved that H bar is a subgroup of G. Okay, so that's the first part. And so now finally, we're going to suppose that there exists a non-empty subset U, which is open in H bar. Now H is just the union of translates of this U. And so because U is open, each of these translates is open, and so H is this infinite union of opens. So this shows that H is open in H bar. And now you apply lemma 2 with those two non-empty open subsets, U and V both being H, to actually get that the algebraic group H bar is HH, which is of course H. And so there we go, H bar equals H. So that's lemma 3. And then finally, what we've been building up to is the theorem that phi be a morphism of algebraic groups. Then the image of that morphism, so phi of G, which is of course a subgroup of H, is actually a closed subgroup of H, hence it's an algebraic group in its own right. So the proof, the proof needs one more fact from algebraic geometry, which again I'm not going to prove. This is just a little bit more commutative algebra than is relevant for what we're trying to do. And that's that the image of any morphism of affine varieties contains a non-empty subset of its closure. So given that, all you have to do is you just apply lemma 3 with so let me see, you just take you just apply lemma 3 to phi of g sitting inside H, and this so the closure of this is a subgroup of H, and it contains a non-empty open subset of its closure, so by that second part of lemma 3, actually phi of g is equal to its closure. And that just does the job. Okay, so images of morphisms of algebraic groups, they are again algebraic groups because they're closed subgroups. Of course, the kernel of a homomorphism of algebraic groups, I mean, that's just the inverse image of the identity. And since phi is continuous, that's closed. And of course, it's normal. So this kind of begs the question, can one make sense? So this is the group G quotiented out by the kernel of phi, and then there's the image of phi. So this is just an abstract group at the moment, right? It's the group G factored out by this normal subgroup. And the question is, can one give this the structure of an algebraic group in some more intrinsic way? More generally, if you have any closed normal subgroup of an algebraic group G, can you give that quotient group if the normal subgroup's n? Can you make G over n into a normal subgroup? And then, is this an isomorphism of algebraic groups? So now we're kind of getting to the place where I'm trying to stop telling you general theory of algebraic groups and move towards Lie algebras. But this first question is very interesting, and the answer is yes. You can there's a canonical way, given a closed normal subgroup n of an algebraic group G, there's a canonical way to make the quotient group G over n into an affine variety, hence an algebraic group in its own right. And the answer to this question is, well, conditionally yes. Yes, if phi is what's called separable, but no in general. Now, in characteristic 0, every morphism is separable. So that's saying the answer is yes in characteristic 0. But if you pass to fields k of positive characteristic, the first isomorphism theorem in the world of algebraic groups has got a conditional in it. You need to add that phi is separable before that becomes an isomorphism of algebraic groups. So I'm not really going to talk anything at all about this stuff. But it's very interesting, and it kind of shows you where you should go next if you are pursuing algebraic groups. Let's just do an example, though. Let's take characteristic 2. Then we've got the special linear group SL2 of K, and then there's PSL2 of K, the projective special linear group. And I mean, I guess the kind of usual definition, there is such a thing, the usual definition of PSL2 is that PSL2 of K is SL2 of K quotiented out by the scalar matrices of determinant 1. So in SL2, that's just the identity matrix or minus the identity matrix. Well, that's totally good. In characteristic not 2, in characteristic not 2, that's a correct definition of PSL2 of K as an algebraic group. Once you've set up how to make that quotient group into an algebraic group in its own right. But I mean, you kind of get a smell that there's something a little bit weird going on in characteristic 2, because in characteristic 2, PSL2 of K appears to be equal to SL2 of K as abstract groups. Because the plus 1 equals minus 1, and so we're not doing anything. But in fact, there's the correct definition of PSL2 of K as an algebraic group. Fixes this issue. So in fact, even when P equals 2, SL2 of K is not isomorphic to PSL2 of K as an algebraic group, though they are as abstract groups. There's still always this quotient map from SL2 onto PSL2 of K, and when P equals 2, this quotient map phi is not separable. And so that's why why the kind of naive abstract group theory definition of PSL2 of K as SL2 factored out by the scalar matrices is kind of the wrong definition in characteristic 2. It doesn't give you the correct affine variety structure on PSL2 of K. Okay, so I really don't think I said enough to make any of that really make good sense, but fair enough. So there's tons of interesting things to investigate in the theory of algebraic groups. This issue that has just cropped up, if you have a closed normal subgroup of an algebraic group G, how do you make that quotient group G over N into an algebraic group in its own right? So you have to introduce some affine variety structure on that quotient. There's even more of an issue if you have any closed subgroup H of an algebraic group G. How do you make the set of left cosets into a variety? That should be possible, right? And it turns out this is possible, but in general it's not affine, so you need to upgrade your algebraic geometry to allow projective or indeed quasi-projective varieties. And this is all kind of closely linked with the question of understanding orbits of algebraic groups. So this starts becoming very interesting. If you have any variety X, affine or not, there's a good meaningful notion of what it means for G to act on X. So this would be an action in the usual sense of group theory, which is also a morphism of varieties, whatever that means. Can you make orbits of G on X? So if you've got an algebraic group G acting on a variety X, can you make orbits, things like G dot X for X in X, into varieties too? Well, if you could, then you probably expect that you always have this orbit map, right? Sending coset. So CG of X is the centralizer of X and G, the stabilizer. And there's always this orbit map sending the coset of the stabilizer to G acting on X. And that's always a bijection of sets. Is this an isomorphism of varieties? And so we would, on the previous slide, we were kind of having to discuss these coset spaces when H was a normal subgroup and you're expecting that quotient to be an affine variety. If you go to more general closed subgroups, there's a way to make the space, that coset space, into a variety in the appropriate universal way, but you have to leave the world of affine varieties. And then you kind of feel like that space of cosets should be related to orbits if you take your subgroup H to be the stabilizer of some point in an action. And again, that turns out to be true in characteristic 0, but in characteristic P, in positive characteristic, that's not necessarily the case, and separability starts becoming an issue in this. So I'm not going to go in and do anything about any of these very interesting questions. Normal subgroups, making cosets into varieties, all of this it uses a lot more algebraic geometry than we want to get into.